Donc, c'est un plaisir d'accueillir Ivana, who's a dear friend and colleague for so many years, too much to tell. But we met at maybe the first symposium talking about interbrain synchronization ever. And it was like, yeah.
Very local.
Very local in Aarhus in Denmark. She's in Denmark. But she got like a very interesting trajectory. Similar, we are very similar actually. It's funny. We have been evolving in parallel in our career, and so she comes from engineering. She did engineering in UFT in Toronto, and she's half Canadian. So it's good also to mention here. Then she moved to UK at Imperial and then UCL, doing a PhD in between the team of Chris Frith at UCL and the team of Andreas Schroppenhorf in Harris. I never know if I pronounce well.
No one can work.
And now she has been since then in Copenhagen, where she did the sine lab, or nice sine waves, for studying social neuroscience in mostly adults, but also now with baby and kids with thoracic case, for instance. And so, like, I'm a big fan of our work, and I'm looking forward for the research and stuff. Thank you, Ivana, for the long way to here and to be with us.
Thanks so much for the introduction, Guillaume, and thanks so much for inviting me and hosting me in your wonderful group today. So today I'm going to talk about social asymmetries, focusing on the interpersonal mechanisms and models of self and other in social interaction. So as Guillaume said, I work within the field of social neuroscience or social cognition more broadly. And as probably many of you know, this field has gone through a large movement in the last decade and a half, or maybe even close to 2 decades now, away from studying individuals in isolation from a social setting or from an actual interaction, responding to just computerized stimuli, towards the so-called joint action approach, so studying individuals engaged in interaction with one another. And the reason for this is because it was proposed that social cognition is fundamentally different when we engage in interaction with other people. And even more recently, it's gone more towards two-person or interpersonal neuroscience, so trying to understand the interpersonal behavioral and neural mechanisms when we interact together. And this is something that's quite challenging. So here, this shows motion tracking of 2 people giving each other a hug. And it literally looks like they're crashing into and over each other. So from a data perspective, it becomes quite difficult to quantify something even so simple. And for that reason, this has been coined the dark matter of social neuroscience, or rather studying interpersonal dynamic interaction has been coined the sort of dark matter. And where we want to go, and you'll see our very early attempts to go, is towards also studying group social mechanisms in social networks and across different time scales. And so why is this interpersonal important? Well, in the African Bantu language, the word Ubuntu means that a person becomes a person only through other people. And in neuroscience, we know that the brains and our sense of self is shaped through our interactions with other people. And more recently, Victoria Southgate, whom Guillaume also mentioned, who's a dear colleague of mine, has proposed that infants are born alter-centric. So they're born focused on other people, and that the self emerges only later in development through our understanding of other people. And so what I'm particularly interested in is how this we emerges from the dynamic and reciprocal coupling of self and other in interaction, and what the underlying mechanisms are. And the framework I mostly work within, although we're starting to go into more ecological domains of verbal interaction, but so far I'm going to talk about nonverbal social coordination and synchronization. So we're capable of coordinating our actions together with other people extremely precisely, and this can be both intentional and unintentional. So for example, synchronized swimmers are sort of expert coordinators. They can synchronize with each other at very short timescales. But as you probably noticed, if you are at a opera or a sports event, when people begin to clap, they quickly fall in sync with one another, even without the explicit intention to do so. So this is also something that happens spontaneously. However, interpersonal coordination is not always symmetric. So oftentimes it requires different tasks and different demands between individuals, and these are implicitly balanced. So a large body of joint action research has studied coordination mechanisms and shown that coordination is facilitated by real-time prediction of others' actions, but also predictability of our own actions. So when we interact with others, we also make ourselves more predictable, and this can be both intentional and unintentional. Furthermore, by signaling, so we exaggerate our own actions to communicate a goal. So for example, parents will exaggerate their own actions to signal the goal to their child or their infant. However, much of this research has once again focused largely on like individual mechanisms rather than interpersonal. Which doesn't tell us about the interpersonal differences and factors that might influence coordination. There's also decades of behavioral studies which have focused on the temporal dynamics of interpersonal coordination. An old study from Mike Richardson, for example, which had people sitting in rocking chairs next to each other, showed that even though people were not instructed to synchronize, that they tended to fall into sync with one another when they could see each other. And this happened even when the natural frequencies of the chairs were different, so if they put weights on one of the chairs. And this has been shown across a wide range of studies. For example, these finger flexing studies showing that when people can see each other, they fall into sync with each other spontaneously. So they're sort of like the pendulum clocks that Christian Huygens originally observed, except that the coupling medium is visual or auditory or other, through other sensory modalities. And it happens across other modalities as well. So I won't talk very much about interbrain synchrony today, but I'll briefly touch upon it. But it also happens, for example, across postural constraints when people engage in interaction with one another. What's been less explored, again, is how differences in the context of role asymmetries or social asymmetries may modulate coordination dynamics. So there's been a large focus on synchronization and symmetry. But just to give you an example of what I mean, some of the work by Alan Wing has shown, for example, that different roles, for example, in a string quartet, can drive different patterns of adaptation between members. So for example, in this study, this particular quartet, what they found was that violin 2 will mutually, I won't go into details of these plots, but mutually adapts with the viola and the cello, whereas with violin 1, there's a more asymmetric relationship with the other members of the quartet, where the viola follows, but violin 2 and cello lead. And this can also change from quartet to quartet. In addition, a very now quite old study from Richard Schmidt and colleagues looked at how asymmetries in social competence can affect interpersonal coordination. So in this case, they recruited pairs who had either both members had high social competence or both members had low social competence, or one had high and one had low. And what they found in particular was that the heterogeneous pairs, so the ones comprising of a person with high social competence and one with low, coordinated better, or rather more stable than homogeneous pairs, particularly at the faster frequencies. So in other words, a person's personality characteristics become embodied in their motor behavior, and these traits constrain the synchrony of their social interaction. And so today I'm going to talk about different social asymmetries. In other words, the interpersonal, social, relational, and task-related factors that modulate how we coordinate with one another. And investigating such social asymmetries can probe into the underlying mechanisms and models of self-other integration when we engage in social interaction with each other. So they're incredibly important and I think quite understudied. So I'm going to go through a series of studies. So please stay with me. Looking at first the effect of task-related factors on self-other coordination dynamics. So in other words, looking at how symmetry versus asymmetry in task demands can modulate social coordination, how relative feedback or the amount of reciprocity between people can affect coordination and the role of task-related expertise. And then I'll also talk about how high-level social interpersonal factors, such as interpersonal differences in how we connect to and with others, for example, in social networks, can have an effect, friendship dynamics, and also social relationship and group membership. And finally, I'll briefly touch upon how social asymmetries can drive different underlying neural mechanisms, some of which is still quite preliminary work. So when I first got into this field, it was a lot more exploratory. There weren't that many people doing interaction studies. And so we were interested in how, for example, by manipulating the feedback that two people had of each other, how this can affect coordination dynamics. And so we designed a fairly symmetric tapping task where we had two participants that were seated in separate rooms, and they were given a metronome, which was giving a stimulus through their headphones, which was a metronome of at 96, 120, or 150 beats per minute. And following this, the metronome would cease, and they were instructed to tap and synchronize with the auditory feedback. And then we manipulated the auditory feedback, so sometimes they just heard themselves. So it was a self-paced tapping task. Or they were unidirectionally coupled. So for example, I heard myself, you heard me, or bidirectionally coupled, where I heard you and you heard me, or a mediated coupling where they both heard a metronome. And so what we found was quite robust patterns of coordination. So in this unidirectional coupling task, what we saw was that in this task, we're both hearing member one. So member one is just self-paced tapping, and member two is adapting to member one. And what we see is that the intertap intervals oscillate on a tap-to-tap basis. The intertap intervals of one person sort of oscillate around intertap intervals of member one, meaning that they adapt to what the other person did on the last tap. So if member one went faster on the previous tap, then member two would speed up, and if they went slower, they would slow down. And so we use these windowed cross correlations to measure this, so not treating the two signals as completely stationary, but as if they have local stationarity. We find this continuous lag +1 cross correlation and lag 0 negative cross correlation, which means that member two is basically synchronous with member one's previous tap. And interestingly, in the bidirectional condition, what we see is that their intertap intervals oscillate on a tap-to-tap basis, so they mutually adapt to one another. So if I went faster on the last tap, you will speed up on the next one, but I will simultaneously slow down. So we see these continuous lag +1 and lag -1 correlation coefficients and a negative lag 0, which indicates that two people are sort of like hyper followers of each other. And no matter how long they do this task for, so if they do it for I don't know, 15 seconds, or they do it for 5 minutes, we still see this pattern of behavior. And so we don't see also an emergence of a leader in this case. Even if people tell us, for example, I was definitely the leader of that interaction, they're followers. And when we looked at how well people coordinated, so how much this had an influence on how well they synchronized with each other, what we find that in the bidirectional condition, they were just as synchronized with each other as when they heard a completely regular metronome, but the synchronization suffered in this unidirectional situation when one person was both variable and unresponsive. So in other words, what we concluded was that coordination is facilitated both by prediction of the partner's subsequent action and also mutual adaptation mechanisms. However, what we've been interested in is what happens to coordinated behavior when the difficulty of one of the individuals is manipulated. So as I said, coordination is not always symmetric. Sometimes people have to produce complementary actions, and sometimes they take on complementary roles of a leader and a follower. And so together with my colleague, Joshua Skews, we wanted to study the effect of task demand asymmetry on the self-other coordination mechanisms. And so we recruited, once again, pairs of participants, except this time they had a clicking task. So they were given both a visual stimulus and an auditory stimulus. So the auditory stimulus was, again, a metronome that they received, and they were instructed to click at this particular metronome, but we manipulated whether they had feedback of themselves, of the other person, or of the metronome the whole way through. And they were asked to click between these two spaces between the rectangles. And what we did was that on each trial, one person was assigned the role of a reference. So they had the widest possible targets, and the other person was a target, which meant we made the task more difficult by making the width smaller. And they were not aware of this manipulation, so that the other person had a different task for them. So importantly, they don't see what the other person sees. The only feedback they get is of the other person's clicks. And so once again, when we look at the symmetric task, so in the case when the reference and the target are the same, they have the same width, we once again see this pattern of mutual adaptation between them, that they mutually adapt to one another. But interestingly, when the task becomes more difficult for one person, then one person takes the role of a leader implicitly and the other of a follower. So can you guess which person leads and which person follows in terms of task difficulty?
Difficult is a leader.
The difficult is the leader, exactly, because they become more self-focused, focused on their task, whereas the follower focuses more on the coordination. And so we wanted to see how whether this facilitated the coordination in any way. And we looked at how these leader-follower dynamics affected the performance of the task, which was the synchronization. And what we found was actually that the synchronization was better with an adaptable person than with a completely regular metronome in this case, irrespective of the index of difficulty. And this was achieved by this leader-follower strategy, which is implicitly negotiated. So in other words, while in the case when task constraints are symmetric, we see that coordination is facilitated by mutual adaptation. When people have asymmetric task constraints, then it seems to be facilitated by this implicit negotiation of leader-follower roles. So far, it seems that bidirectional feedback, or reciprocal feedback anyway, is very important, but we wanted to also further test how important is reciprocity or bidirectional feedback for interpersonal coordination. So as I said, as I just showed, a lot of the previous work suggests that reciprocity is best, meaning that people coordinate best when information flow is bidirectional, because then they can mutually predict and adapt to each other. But there's also, but previous work also suggests that bidirectional information flow is not as important if the partner is completely predictable. And there's some studies, one study by Hart and colleagues, which shows that people also become more predictable when they engage in reciprocal or mutual interaction with one another. In this case, they sort of had to do a motion task or the mirror game task, and they converge on kind of a universal stroke of motion when they do it mutually together. So we wanted to directly test whether interpersonal coordination is facilitated by the mutual reciprocity between partners, so meaning that bidirectional feedback is necessary, or through emergence of more predictable patterns during the bidirectional interaction. So meaning that it would only be necessary for one member in the pair to be in the bidirectional interaction. And so we did this extremely ecological study. No, I'm joking, it's not ecological. We had two people in separate rooms that were asked to breathe together in synchrony, but they only received visual feedback of the other person's breathing rhythm. And so basically, we recorded respiration from the two people, and they were they engaged in a bidirectional interaction, so where they both see each other's breathing signals, and they have to synchronize in real time. So it's a biofeedback task. or they engage in a unidirectional interaction, which means that they breathe to a signal, breathing signal from a confederate who's seated in a room and has no visual feedback on anyone. So they're just asked to breathe at rest. And then in a follow-up experiment, what we did was we took the signals, the breathing signals that emerged in this bidirectional condition, and we fed them to a new set of participants in a unidirectional case that were just given the same instructions, like breathe with another person in synchrony. You'll see their breathing signal in real time, but they didn't know that this was just a recording from this condition. If you have questions, please ask. So in other words, what the breathing signals look like is they're just these sinusoids. So when they inhale, they go up, and when they exhale, they go down. And in the bidirectional interaction, they seem to be quite phase locked and synchronous. Also in the unidirectional interaction, they seem to just lag behind the confederate a bit. And so what we did was to test this hypothesis. We looked at the phase between the two signals and what the distribution of relative phase was. So we extracted phase from each of them, and then we looked at the relative phase distribution. So basically, this shows if there's no synchrony, we would see a uniform distribution from minus 180 degrees of relative phase to plus 180. But if there is synchrony, then we would see a peak somewhere, and if they're in phase, we would see a peak at relative phase of 0. And so what we see, unsurprisingly, is that people are more in phase, however, less phase locked. So this peak is higher, meaning that they're more consistently at this lagged phase. But they're more in phase but less phase locked when feedback is bidirectional versus unidirectional. But interestingly, there's no difference between the bidirectional and control condition, meaning that people are just as synchronized in the offline interaction when they're breathing with a non-responsive partner who was in an online interaction with one another. So it seems like reciprocity is not as important as we would like to think it is. And so further, we wanted to see whether this synchronization was facilitated because more predictable patterns of breathing emerged when they were in the bidirectional condition. And so we looked at different parameters of breathing. First, we looked at the effect of breathing frequency, and what we found was that when people were in the bidirectional condition, the slower they were breathing, the more in phase synchronized they were with one another. And similarly, in the control condition, the slower people were breathing in the bidirectional condition, the more in phase the control group of participants, the new set of participants synchronized to them. So it seems like the slower breathing facilitated interpersonal synchronization, meaning like making the signal is perhaps more predictable in real time in terms of like aligning to the changes in the signal. But we also looked at the effect of the stability of the breathing frequency, and that was because what we found in the unidirectional condition is that the confederate, unsurprisingly, was a super stable breather because they were just breathing at rest. So we thought maybe that's why people were more phase locked. So we wanted to see how much this had an effect. And so this is and there was a big variability in people in the bidirectional condition. So this is a breather that's changing their breathing frequency. So in other words, they start out quite fast and then they slow down, they speed up again, and they slow down again. So we extract the coefficient of variation of the dominant breathing frequency across the interaction. And what we find indeed is that in the bidirectional control conditions, they are more variable in their breathing frequency than in the unidirectional. And the more variable they are, so the higher the coefficient of the respiration frequency, the less phase locked they are. So in other words, the stability in the breathing frequency facilitates the stability of the coordination. So what we found, just to summarize, and I hope you are with me, is that real-time alignment of breathing rhythms was higher but less stable when information flow was bidirectional than unidirectional, but it was just as good when participants coordinated to a replay of respiration rhythms from the bidirectional interaction. And synchronization of breathing rhythms was associated with slower breathing rhythms and less variable breathing frequencies. So what we concluded was that interpersonal synchronization was facilitated by the emergence of predictable breathing patterns, breathing rhythms, rather than the mutual reciprocal adaptation. Okay, since people have always asked how much task-related expertise plays a role, this is something that I think we've also been meaning to investigate much more of. And Ole Adrian Hegley, who was a PhD student at the time, wanted to see what the role of expertise is in interpersonal coordination and how this can further manipulate the coordination dynamics. And so in this case, he recruited pairs of expert musicians in a polyrhythmic task, which I won't go into the details of, which was quite complex. So it's only something expert musicians can actually do. That's why I can't describe it, because I'm not one. And they engaged in a bidirectional interaction. There were also other conditions. And just to remind you, in the previous studies, what we found in non-expert musicians was that this pattern of mutual adaptation of high lag +1 and lag -1 correlation coefficients. But what Ole found in this study was there were 3 clusters of interpersonal strategies, meaning that there was one cluster of musicians who seemingly did not coordinate at all. So they had 0 correlation with each other, and 2 clusters of musicians that were mutually adapted, but to different degrees. So interestingly, all groups of musicians performed well on the coordination task, and there was no difference between the clusters. But can you guess what type of musicians are in cluster 1? Yes, the drummers. And Ole called this the leading strategy, which was solely found in the drummers, actually. So they were like 2 metronomes, basically. They did not interact, but they were perfect at keeping the beats. So if you look at the data, they look very synchronized, in fact. And mutual adaptation was found in all the other groups of expert musicians. So it seems like expertise gave more flexibility in negotiating these interpersonal coordination strategies. And so what we became interested in further was how these interpersonal strategies actually modulate self-other integration. And we've been doing a lot of tapping studies at that time. So we had quite a lot of data, and Ole really wanted to model this data to study theoretically how this influences self-other integration. So he modeled each person using two coupled oscillators. So one which represents perception and one represents action. So this is theoretically speaking. And these are intrinsically coupled. But in addition, the 2-person units are coupled so that the action oscillator of one person is unidirectionally coupled to the perception oscillator of the other person, and vice versa. The action of the other person is unidirectionally coupled to the perception of the one person, which represents the extrinsic flow of information. And so this model is based on the Kuramoto model of coupled oscillators, with the exception that the connection strength between each pair of oscillators is defined by this coupling matrix K. So basically, when we simulate this data and fit the model, what we get out for each of the different strategies, so whether they're leading, uncoupled mutual adaptation, or leading following, is the strength of coupling. So the units in this coupling matrix that best describes the data. So whether they are more self-coupled or coupled to the other person, whether they're integrating or segregating. And so if we look at how this is, so I'll just summarize how the fits look. So basically the leading strategy, unsurprisingly, leads to also high within-person coupling. So within the self-perception and action oscillators, and low between-person coupling. But interestingly, mutual adaptation leads to high between-person coupling, which is what we expect, but low within-person coupling. So they seem to sort of decouple their own action perception oscillators in order to couple to another person. So in a sense, this is purely theoretical. We've been sort of doing a bunch of studies to see whether we can find evidence of this in other signals, but I'm not going to talk about that today because it's a bit more complex. But what we found here was that expertise and interpersonal strategy therefore modulated the balance between self-other integration versus segregation. Yes.
I want to make sure I understand what within person conflict is. So I understand this is a model of humans. What would be like?
Yeah, so we actually we had this very strange result, which I decided to keep out for the sake of time and complexity today, and I'm still trying to make sense of. So in the breathing and the study where two people were breathing together, what we actually found was that when they're mutually breathing with each other, their own cardiorespiratory becomes uncoupled. And I'm not sure what that means. If that means that sort of them getting into another person's rhythm sort of has an effect on their own self-regulation. I don't know exactly what it means. I think so far the only study that I've seen that kind of conceptually goes with this finding is looking at self-regulation in terms of scores when people synchronize with one another, showing that people rate lower on self-regulation.
So what is the self-conflict? Respiration. What is?
So we know that for example, the respiration is weakly coupled to our own heart rhythms.
Respiration?
Yes,
Yeah.
sorry, the respiration and heart rate become decoupled. Yeah.
In the case of tapping, that may be also like, for instance, in the general model of comparator
Yeah.
models, like how you have your afferent copy of your own action.
Mm.
And so in that case, you may weight more like the action of the other person rather than your
Yeah.
own reafferent motor input, in a sense. I mean, it's a.
So I think it also has to do with self-monitoring, that you are less monitoring yourself when you are integrating with another or when you're synchronizing with another. I mean, we also have some results on functional connectivity, but I'm leaving them out for today, also because I'm not convinced. Yeah. Yeah, so furthermore, what Ole was also interested in, what we looked at was what the effect of these interpersonal strategies had on the individual neural mechanisms. And so here, what we did was we contrasted these pairs were in the leading condition with the pairs who engaged in mutual interaction. And we used a method of dynamic functional connectivity called LADA, which is leading eigenvector dynamics analysis, which detects phase-locked oscillatory patterns that emerge across brain networks. And what it does is it finds the most prominent brain network at any given time. And so, looking at transient brain networks. And so what we found was when we contrasted these two conditions, one particular, your favorite brain network emerged, the right temporoparietal network. And basically what we found was that there was a difference in occurrence probability between the two groups in this network. So in other words, that mutual adaptation exhibited a more frequent occurrence of phase-locked activity only in alpha within this transient right temporal parietal network than leading. And since we know that this is implicated in action perception, processing, and coupling, we speculate that mutual adaptation recruits more neural mechanisms underlying action and perception, which are required for self-other integration. Okay, so now I've talked quite a bit about how am I doing with time?
Oh, you're
Okay.
good, you're good.
About the effect of task-related factors, and I want to talk a little bit some much more preliminary work, which is on how high-level social interpersonal factors can affect coordination dynamics. So something that I've become quite interested in is how differences in higher-level social factors modulate coordination dynamics. And there's quite a bit of literature that shows that interpersonal synchronization and joint action outcomes are facilitated, for example, by social cognitive skills, so by social skills in children, by degree of autistic traits or pro-social versus pro-self orientation, perspective taking, and empathy. However, many of these studies, again, focus on the individual differences, so how an individual's differences affect coordination, but we know coordination is interpersonal. And so something that's been severely unexplored is how interpersonal differences, how different grouping of pairs has an effect. So for example, looking at friendship dynamics or interpersonal diversity in the context of interpersonal differences in social cognitive skills and culture and group homogeneity versus heterogeneity, how this affects coordination dynamics. And so we have a large project that started not super long ago, where we're looking at how coordination mechanisms are affected by interpersonal differences in social network dynamics. And so in other words, how we define interpersonal differences in the case of the first study I'll present is the relative differences in how we connect to and with others. So in other words, differences in the social network properties between two people who are part of the same network. And so what we're interested in is whether relative differences in these social network properties are also embodied, modulating low-level coordination mechanisms between interacting partners. And so first, we did this pilot study some years ago, and this is sort of what kicked off this project. And I call it a pilot study because it's quite undersampled, and we want to replicate it, but it was done with a very special network. So it was done in collaboration with my colleague Sune Lehman, who works on social networks. And at the time, he was mapping this amazing student social network, where basically he gave out like 2,000 mobile phones, or the 2,000 students received a mobile phone, and he tracked them for a period of 2 years, basically tracking their physical proximity with high resolution, their Facebook friendships interaction, their text messages and phone calls. But basically, this was before GDPR. And so I thought this would be feasible to do something. So, and now we're doing it in much lower resolution. But at the time, just before this network sort of graduated and disappeared, we pulled them in to do a study, and we hope to get more of them than we did. And what we did was we varied the asymmetry and eigenvector centrality between pairs of participants. And so there's also a recent study from Sievers, which I'm not sure it's been published yet, which showed that individuals with high eigenvector centrality are more likely to adapt to the group. So we thought this would be an interesting measure to vary between people as best as we could. And we controlled whether they were friends or not. So we had 3 groups just as a control, but it was quite undersampled, of close friends, Facebook friends, and non-friends. And so they did a very low-level task. It's because at the time we also scanned one of them, and they had to do this force production task where basically they were given a visual circle on each trial of a target force. So the bigger circle, the bigger the force they had to produce, and then they would receive either real-time feedback or they had to guess. Their task was to meet this target force together by pressing on a force-sensitive resistor, but they received continuous feedback of the joint force. So in other words, they don't know what their own contribution is in relation to the partner unless they're not pressing at all. They can only infer this. And we did this both with and without continuous feedback. And so just to give you an idea of how the data look, so they're quite simple. So over 4 seconds, the raw force data, they tend to overpress, and then they sort of quite quickly saturate and meet this target force and oscillate a bit around it. And so first, again, we looked at whether we could find just coordination dynamics overall across diets. And indeed, we found this mutual adaptation, which is now flipped, meaning that we see this negative correlation for both people. So in other words, when one presses too much, the other one releases, which makes sense. So they go in opposite directions. And so what we wanted to see was whether the relative centrality between the 2 participants was associated with the relative coordination dynamics, meaning how much force they contributed or how much they adapted. And indeed, we found an association in this pilot study. So we found that the more central, so this is the asymmetry and centrality. So the more central they are in relation to the partner they're interacting with, and they know who the partner is, I should say, but they don't know what their centrality is in the network, although presumably they could infer it, the more force they contribute to the task. And the more central they are, the more variable, the more adaptable they are also in relation to the partner. In other words, this interpersonal difference in centrality seems to constrain their relative force and coordination dynamics. So the interacting partners in this case seem to embody their relative social network properties into their motor movements, which modulates the coordination dynamics between them. And they do this irrespective of the social relationship. So we see a very stable relationship in asymmetry and centrality and asymmetry and coordination across close friends, acquaintances, and unaffiliated pairs. It's just the only difference is that they're more similar in centrality with their friends. So it's a steeper association. Yeah, I have a plot if you're interested, but it's very understood. And so what we've been interested lately, so we're doing a lot of follow-up studies and we're still in data collection, so I don't have results to present yet, but we're looking at how these mechanisms are modulated when social dynamics also become more complex, for example, in group interactions. So at the moment, I'll present some preliminary results from a study that my postdoc Lee has been conducting, looking at the effect of friendship dynamics on group coordination. And so what we're doing across these studies is that we're mapping social networks among bachelor students using questionnaires. So we're not tracking, we don't have any data from their mobile phones. I don't think we can do this anymore. So it is much more low resolution. We have to rely on self-reports. And what we do is then we recruit them once we map the social network, we recruit them in triads, where two of them are close friends and one is a non-friend from the network. And what they do is they once again engage in a similar force production task, except now they press like this instead of like this because it's easier. They get less tired. And then we record EG, and I don't have this the EG data yet. So basically they get a target force and then they receive a continuous feedback of a joint force of all three, or they have to guess and they only receive feedback at the very end. So in other words, it's more like a prediction task. So in other words, they don't know what their individual contribution is. They infer that, but they know who the other two people are. Yes.
So just to make sure the definition of friendship in this
Yeah.
context is that somebody that is within a network.
It's reciprocal that they reciprocally rate each other as close friends. So they tick off in the class we take a list of all the people in a bachelor education, and they have to check off all their close friends and their friends from the class. And so we recruit the ones that reciprocally rated each other as close friends.
It's in Denmark.
It's in Denmark, yes. And the third one is
Which may be like a big cultural
yeah, sure,
factor.
sure.
Like in the US, for instance, the notion of friendship.
Yeah, so we give them definitions, actually, which rely on literature. We provide definitions of close friends and friends so that everyone relies on the definitions, but I cannot say whether they actually do that. Yeah.
The grading?
It's not grading. No, we keep it very simple. They just check. They go close friend, friend, and if they're nothing, they don't check them off.
So it's fine, basically.
Yeah.
Close friends.
Yes, exactly. Yes, we had a year of discussion about this.
No, it means.
Sorry?
No enemies?
No, we don't look at enemies. No. No, I can't tell you how many ethical issues we already had in getting this up and running. It like took a year to get all the ethics approved and a year of discussions on how to do the questionnaires. So we converged on this simple, where we provide them definitions, close friends and friends, and the rest are not rated. And yeah.
Hypothesis here would be that close friends would coordinate on a task like this better than.
That was our hypothesis, but it's not what we're seeing. And so I should say we are doing data collection right now, which means that I only have data from 13 triads, but there is an effect that looks we're hoping it's robust. So this is super preliminary. So what we find is that in terms of the force, the non-friend contributes more, whether they have feedback or not. The non-friend works harder at the task. And it's quite funny because since we found this data, Lee and Kivelli, who are postdocs in the group and who have been doing data collection, they said that so many times the non-friend would come out of the experiment and go, my hand really hurts. And the friends would go, really? I don't really have that experience. So it seems like the non-friend contributes more force to the task than either of the friends. But I mean, this is preliminary, so we'll see if it actually holds up across people. The non-friend also reaches the max force faster, so they sort of are very eager to press on the task, which might be why this happens, but then adapts slightly less to what the other people do. So the friends seem to be a bit more adapting in the task, but they definitely contribute less so far, it seems. So this is just.
They know within the triad, sorry to interrupt, but they know within the triad that they've been recruited as the non-friend.
They don't know, they are not told explicitly.
I mean, there's a group of.
Yeah,
people,
sure,
and people know these two.
Sure,
working out
yeah.
together, so clearly I'm the
Yeah, but they don't know who's contributing what. So in other words, you could easily free ride without anyone knowing. So it's implicit, right? Because you only get the joint force. Although we have some more manipulations, but I won't get into them because I'll wait till we have the full data. So in other words, they appear to embody the social group dynamics into their social behavior. And we have a lot of, we're doing a lot of studies with the social networks right now, a lot of interpersonal coordination because we are doing EEG, so it needs to be quite low level. So hopefully we'll have some more results coming soon. But lastly, before I get to the brain mechanisms, I wanted to talk about a little bit because of course, these social high-level factors are super complex and there can be different effects. I wanted to talk about how social relationship and group membership can also affect coordination in an implicit sense. And so this is an old study now that I thought I would include because I think it's relevant, looking at embodiment of social relationship and social networks in a real world setting. So this was done with a very different approach and idea in collaboration with a group of anthropologists who were interested in high arousal rituals. In other words, because high arousal rituals are quite puzzling because they're very costly to the individual, they can get hurt, but they seem to be very prominent anyway across societies. And so there's sort of a century of observations from anthropologists showing that rituals foster assimilation, enhance group cohesion, and that they strengthen bonds between members. And so we were interested in actually measuring something physiological in the real world and seeing whether we could tie these field observations to a physiological basis. And so what we did is we went out into the field in a spire walking ritual in Spain, and we measured heart rates from people crossing the fire and people observing, so the spectators. And we measured heart rates of two groups of spectators, ones who were related to the firewalkers, so either like a close friend or a family member or a wife or husband and so on, or child, and an unrelated spectator. So again, it's a real world study, so everything's chaos and we did the best we could. But basically what we found was looking at the raw data, already we could almost qualitatively pick out who the firewalkers and related spectators were because they had huge deviations in their heart rates. So this is the heart rate of a firewalker. This is the time where he crosses the fire and you can see the heart rate goes up. And this is the time where his brother crosses the fire. So it also goes up. And we see a very different pattern in his wife. So her heart rate goes up when he crosses the fire, and interestingly, a little more when his brother crosses the fire. And then we look at the non-related spectator, and there was much less response, except for at the end here where they all stand up. Or that's what we think is happening. And so we used, in order to measure the shared dynamics between these signals, we used cross-recurrence quantification analysis, which is a nonlinear method that measures the shared dynamics and coupling between signals. And I won't go into a lot of detail, but it's based on recurrence or shared recurrence in the case of cross-recurrence. And so we extract a bunch of variables in terms of the coupling parameters. And overall, what we found was that the coupling in heart rhythms was found between firewalkers and the related spectators, but also firewalkers and the marginally related spectators. So the ones, what the marginally related group means is that they're related to someone else who is participating in the firewalk, but not necessarily the firewalker that they're paired, not the firewalker that they're paired with. In contrast to the non-related spectators, which was higher during the ritual in contrast to the baseline. And this is despite, I should say, importantly, despite difference in bodily behavior, because the spectators are just sitting and watching the firewalk. So in other words, it shows that interpersonal physiological coordination is modulated by the social bonds, but also by the group membership, because there was no difference between pairs who were related and those who are marginally related. So as long as they had kind of a membership in this community that participates in the firewalk, we found synchronization between the spectator and the firewalk. Okay, I hope I'm not going too over time. At the end, I wanted to talk a little bit about how these social asymmetries can drive different underlying neural mechanisms. And so I'm sure all of you know work from Guillaume Dumas, among others, that have looked at interbrain synchrony. Now there's, so Guillaume has been part of the pioneering of this work with dual EEG, but now there's quite a lot of work showing also that evidence of interbrain synchrony during motor synchrony and during other types of social interactions. So in this study, what Guillaume found was that when people were behaviorally synchronized in a task where they had to both improvise and mirror each other's movements and synchronize with one another, there was also more interbrain synchrony in alpha mu rhythms, in beta and in gamma. And so you can see the interbrain pattern here, which looks somewhat symmetric, but I guess it's not always symmetric. Often it can also be asymmetric.
Yeah, kind of in the high frequency types.
Yes, in the high frequency. Yes. And now there's quite a lot of work also showing that interbrain synchrony emerges even when people from behavioral synchrony, even when people are not instructed to do anything together, but they don't have a particular task, but they have visual feedback of each other. And so what I've been interested in particular, in the context of hyperscanning, is interbrain asymmetry. So in other words, how we can use hyperscanning to probe neural mechanisms that underlie asymmetric task and role-specific mechanisms during social interaction, and learn more about the underlying neural mechanisms. And the reason I became interested in is because the first study I did, which was actually aimed at looking at interbrain synchrony, turned out to give us unexpected behavioral results. So in this task, which followed up our behavioral studies with joint finger tapping, we measured EEG from two participants doing a very simple synchronization task. They either heard each other or they heard computer metronome. And we wanted to contrast these conditions. But what we found, and these were very short trials, what we found actually in this case was that leader-follower roles emerged in all but one pair. So there was always seemed to be kind of a prominent leader and follower in the pairs. And when we looked at the individual brain data, when we contrasted the interactive with the non-interactive condition, we found a suppression of the mu rhythm, so sensory motor 10 Hertz oscillations, which were both suppressed because they're doing a motor task when they interact with the other person and with the computer, but more suppressed in interaction with the other person. And these were both left centroparietal, so contralateral to the hand they were tapping with, but also somewhat frontal. And what we wanted to see, since these leader-follower roles emerged, in particular with, can we use this two brain data somehow to better decode what is happening based on the roles. So we did it in a very data-driven way. We used a multivariate classification where the embedded were the 10 Hertz power across all electrodes of person 1 and all electrodes of person 2. And our classifier, we had two different conditions that we tried to classify from. That was the interactive condition and the computer condition. So it was quite simple. And what we found in this case was, and this is just representative of one pair, but it was robust across all of our pairs, was that the frontal electrodes of one person emerged as good classifiers of the interactive versus computer condition. So always one person's frontal electrodes, and this happened to be the leader in all but one pair. So in other words, if you think about what they're doing, the follower is following another person in an interactive condition. This is at least how we interpret the data, and also following the computer condition where the leader has to do something different in the interactive condition. So they have to decouple from the other person and focus more on their own movements. And so we find that the leader's frontal electrodes are picked up as best classifiers of interactive versus non-interactive conditions across all but one pair with quite high accuracy. And this also, we can even see this on the period before they begin tapping. So in the preparation period, it almost seems like the leaders decide whether they would, or I'm speculating now, whether they will lead the interaction. So in other words, we interpret this as leaders investing more resources into planning and control of monitoring self-generated action. And more recently, we became interested in new hyperscanning methods as well. And so Lee, who is a postdoc in the group, had previously done a PhD, which was on biomarkers, and he'd been working quite a lot on with microstates. And so he had this idea, why don't we do two brain microstates to the data in a study. In other words, what we were interested in doing was because this can tell us something both about the interbrain synchrony, but also the asymmetry. So microstates are quasi-stable brain states, or topographic maps, which have been found prominently in resting states. So they correlate with resting state networks. And they're quite prominent microstates that emerge if you look at resting state data. But what we wanted to do was we wanted to fit this to interaction, the different task conditions during interaction. So just to show you a video of how this looks. So this is, of course, slowed down quite a lot because they're very fast. This is just, I think, maybe 1 second of data. But basically, the way we did this was we were interested in whether these microstates are not constrained to have the exact same. So the two people are not constrained to have the exact same brain activity, but rather, which you can also see happens very rarely, one microstate consists of a stable configuration of specific activity in participant 1 and another activity pattern in participant 2, which both occur together at the same time. Of course, we also try to do it so that they are in the same state at the same time, but there was nothing there. So, and so what we did was we fit these microstates to an experiment from a mirror game paradigm, and I'm not going to present the results of this today just for lack of time. We had two people improvising and synchronizing movements, and we record EEG both in a resting state condition, also in an uncoupled condition where they cannot see each other and they produce independent horizontal movements, or in a coupled condition where they see each other and they synchronize, or a control condition where they follow the same the stimulus movement, but they don't see each other, or two asymmetric condition where one person is an observer and the other is an actor. So they're just told to improvise movements while observed by another, or a leader-follower condition. So we had a lot of conditions. And of course, first we tried to just look at individual brains and fit the microstates to see whether we can distinguish the different tasks from the microstates. So they've been very rarely fit to task specific data. They're mostly done on resting state data, but nonetheless, we found very typical resting state-like microstates in the individual data. However, we did not find that the microstate dynamics across individual brains were related to the different interaction conditions. So there was no difference in the different parameters and the ratio of time covered of each microstate and so on. But when we fit them to the two brains, then we found an interesting result, which is that the dynamics of the two brain microstates were different only for the observation condition and slightly for the leader-follower condition compared to all other conditions where participants had more symmetric tasks. So in other words, they seem to have different dynamics when they were engaged in asymmetric tasks. So if you look at the specific microstates, the first one is fitted always to the observer or the leader, and the second one is fit to the actor or the follower. No, sorry, observer or actor and no, I'm sorry, observer. I'm mixing it up now. Observer and follower and yeah, no, I'm mixing it up. Hang on. Observer and actor and leader and follower. Yeah.
Okay.
And so what we found was that, anyway, the more important condition is the observer actor ones. If you look at these look like typical microstates, whereas when one person is in a typical microstate, the other one seems to be in a kind of random state. So in other words, there was no synchrony, in fact, happening in this experiment. But here, the other person, so when the observer spends more time in typical resting state microstates, the actor spends less time in typical, which kind of makes sense because observer might be more in a resting-like condition. But interestingly, we don't see this when we apply it to single brains. So we also looked at whether there were differences between pairs interacting and pairs who were pseudo pairs, the ones who did not interact with each other. And unfortunately, we found the same result in the pseudo pairs. So in other words, the way we conclude this is that the two brain microstates are picking up on more task-related rather than interaction-related asymmetries between participants. So we still match whether the pseudo pair is an observer or an actor, and so on. Yeah. So and this is quite So we're just this is still, or it's not preliminary. We've done a ton of work on this study, and it seems to be quite robust result. But I'm still not sure what it means, of course, and we're hoping to explore it further in other studies. But anyway, just to wrap up, because I think I've gone quite over time, is that self-other dynamics and mechanisms are modulated by various interpersonal factors. So differences in task-related factors, such as task constraints, expertise, relative feedback, but also in social dynamics, are embodied in our movements and our bodily rhythms and modulate the emergent social coordination dynamics between people. And so studying the effects of these social asymmetries on the fine-grained temporal dynamics of social coordination is, I think, important for understanding the social consequences and mechanisms of real-time social interaction. And I also think that development of new interbrain methods that focus on asymmetry may lead to new understanding of neural mechanisms that underlie social interaction and self-other integration. So just as a teaser, because we are also moving into more ecological domains of verbal interaction, Han-Lu He, who just started her PhD recently, is we're interested in interpersonal differences also and other temporal dynamics of other bodily signals and also auditory signals in conversation studies. I just wanted to show a teaser of differences in, these are two strangers who've just met each other and they're engaged in an unstructured conversation. And you can look at their body language. They're not moving very much, but as you probably observed, but this is what happens about 15 minutes into the conversation. So in a later condition. So and this was a pair that this is pilot data, but this is a pair that seemed to particularly like each other. So so there seems to be quite a difference in the mirroring, and we're hoping, we're measuring hand movements and head movements and eye tracking, and also we're interested in the turn-taking dynamics. So we measure the audio from each person. Yes, and finally, I'd just like to thank the team and all of my collaborators and the funding sources, and thanks for your attention.
We have time for a few questions.
I have a quick question on there was a slide that we were showing the dynamics, the brain states of the leader and the follower, and that the follower was basically higher power in the frontal lobe. Yeah, exactly.
No, the leader, the leader has more suppression of 10 Hz oscillations. Oh yeah, I should have explained that better. So there's a stronger suppression of 10 Hz oscillations when they interact with the other versus with a computer.
Okay.
And there's less modulation in the followers. So there's less of a difference between the two conditions. This is just one representative participant, but it seems to be robust for all but one pair.
Do you think there's a reflection between the follower kind of taking in more the sensory information, whereas the leader would be focusing more on what he's doing and therefore kind of planning with himself?
That's how we interpret it. I think of it more as I don't know, I'm speculating here, but the leader, if I think about the task because they are coordinating with one another and they're instructed to synchronize, what the leader has to do is sort of actively decouple from the other person and focus more on their own tasks. And the follower is just responding because it's a very easy task. I mean, it's very automatic to respond, but to lead the interaction and not respond is harder in a way. I mean, you have to actively decouple from the other person.
Do you see like a parallel with like bottom up and top down like processing?
Yeah, so I'm really interested in this actually. I think we're planning some studies to try and distinguish between these two. Yeah. Yeah.
One quick one. Thank you.
Thank you.
Maybe this is a question you get often asked, looking at coupling and uncoupling in couples. So looking at couples that have been together just for recently, just a few months or a few years. Is there data on, have you looked at the coordination of how that changes across?
Yes, we have not looked. Yeah, there is a lot of, from social psychology, I think there's a lot of kind of synchrony data and how it predicts like relational outcomes and all these things. And now I'm having a hard time remembering the specific results. I think there's some data showing that it predicts like relationship outcomes or something like that, but I cannot remember whether it's couples that have just gotten together or have been together for a long time.
So couples that coordinate, but like that have this.
Who synchronize more or have better outcomes or something. Yeah. I don't know. It's
What would be the leading theory that the theoretical work behind this to explain? So, for example, sometimes people are very different, just work brilliantly together as a couple, but they're super different.
sure. And they,
Sometimes people are
yeah.
very similar, actually work together well because they're sort of.
Yeah. I mean, I think it's more about adaptation to the other person. So in other words, it doesn't mean, I mean, this is, I can't remember which signals have been measured. I think maybe it's heart rates or something like that. So it's a basic signal. It probably doesn't say much about whether they change themselves. But I think it's more about responsiveness to the other person. So theoretically meaning like the more responsive they are to each other, the better the outcome. So I'm speculating here. We haven't done any work with couples specifically. We've just started this work with the social networks because we have some control over how long they've known each other. We know they've just entered university recently, but long enough ago that they formed stable relationships. So we try to control this as best as we can. But I think it's very interesting.
You may know the study, I don't remember the name, but where they look at resting state similarity on social network. I think it was
Carolyn Parkinson.
Parkinson, yeah, in Dartmouth.
Oh, that's right. That's right. So there is a study, but they're not interacting. There is a study showing neural homophily among friends, meaning that friends have more similar neural responses and that this scales with the social distance between people. But here, they're not interacting, they're just watching a movie.
Yeah.
So it's how they lock to the stimulus. So in other words, they have more neural similarity in how they lock to the stimulus of a movie. And actually, I mean, some of the social network stuff is inspired from Carolyn Parkinson in that we really wanted to move into the interactive domain and not do these passive tasks of similarity, but see how this actually plays out in a real-time interaction. But yeah, that's true. There is, and I think in general, there's a lot of work there's work from Robin Dunbar that finds a homophily generally among friends. So the more similar people are, or they perceive themselves to be to others, the more likely they are to be friends. But it doesn't say anything about relationship, romantic relationship. Yeah, it's friendship.
Thank you so much for this great talk. We'll continue the discussion with a glass of wine